So the tablet that I use to write when I make these videos is at school, but I want to make this video today. So I apologize in advance for any bad handwriting. That's what I'm blaming it on. To figure out if a function is linear or quadratic, what we can do is look at the first and possibly the second differences. What I mean by that is we look at the outputs. So in that first example in table 1, 4, 6, 8, 10, and 12, and we look for the differences between each of those numbers. So for example, to get from 4 to 6, we add 2. Oh dear. To get from 6 to 8, we add 2 again. Oh, that was better. And then 8 to 10, add 2 again. 10 to 12, add 2 again. And the quality of my handwriting increases the more we write the 2's. As you can see, we're increasing by the same amount each time. There is a constant rate of change. When a function is increasing by the same amount at each step, we have a linear function. So anytime you have first differences that are all the same, your function is going to be linear. Now we can write the equation for this function using an explicit equation or a recursive equation. Let's start with the recursive equation because I think it's a little bit easier. And I'm just going to save us the hassle and I'm just going to type it. So our recursive function is f of n equals f of n minus 1 plus 2. The f of n minus 1 basically means the previous term. So if I'm trying to find f of 4, I'm going to take f of 3 and add 2 to it. If I want to find f of 10, I'm going to take f of 9 and add 2 to it. So recursive just means building on the previous output. Now for the explicit, we have to have a starting value and we have to have a common difference, like what we're adding each time. It's basically the slope. So our starting value here is 4, and then we're adding on 2. We're going to put 2n. That way we're adding on 2 n times. So if I want to find the fifth step, or when n is 5, I'm going to start with 4, and I'm going to add 2 5 times. So that's an example of a linear function. Let's see what happens in table 2. I bet you can guess it'll be different. So to get from 2 to 8, we're adding 6. And by the way, if we were going down, I would write minus 6 there. To get from 8 to 16, we're adding 8. Then we're adding 10. Then 12. And as you can see, we have first differences that are not all the same. So then, if that happens, what we have to do is look at the second differences. So to get from 6 to 8, we're adding 2. 8 to 10, we're adding 2. 10 to 12, we're adding 2. If your second differences match, then what you have is a quadratic function. So what we have in table 2 is an example of a quadratic. Now, for the time being, we're not going to write explicit equations of quadratics. We're just going to write the recursive equation. The recursive equation starts the same way. It's going to be f of n equals f of n minus 1. So you're saying the next term is the previous term plus something. But with quadratics, we're not adding the same thing each time. Here we added 6, then 8, then 10, then 12. But maybe you noticed those numbers appeared somewhere else. So it kind of looks like what we're adding here is not a number. We're not adding like a constant each time. We're adding basically a linear. It's like changing. We're adding 6, then 8, then 10, then 12, etc. So to write the equation, like I said, f of n equals f of n minus 1. And then instead of a number, we add on a linear equation. Now the way you find that is you take these numbers here and you find the linear equation for those numbers. Now in this case, it just so happens that those numbers appeared in the previous example, and that was very convenient for us. We happened to know that 6, 8, 10, 12 was the equation 4 plus 2n. But let's just say we didn't know that, or maybe we didn't notice it. Here's what you would do. So we focus on just this column, and I can see that step 1 is 6. So I'm basically ignoring this stuff right now. I'm looking at these new numbers that I wrote, the first differences. And I see step 1 is 6. I see that 6, 8, 10, 12, this is increasing by 2 each time. So this time I have a starting value of 6. I'm adding 2. And last time I said n, over here, 2n. But this time I'm actually starting at step 1. So I'm going to put in parentheses n minus 1. And that's just in general what you would do if you were starting at step like 5, for example, you would say n minus 5. Now I can simplify this. I can distribute that 2, make this 6 plus 2n Oh my God, this is excruciating.
3 hours later.
So you can see I've distributed the 2 to both of these terms. And then if I simplify this,
1 eternity later.
oh my gosh, that's amazing. It's the same equation. Another way you could have gotten there is you could have looked at 6, 8, 10, 12 and thought, okay, well, if 6 is step 1, I can just kind of go backwards a step, and I would know that step 0 would be 4. And you could just kind of fill that in using logic. That's how you figure out the linear equation, and that's what you add on in your recursive equation for a quadratic. You know what? That handwriting could have been worse, you know?